Welcome to Maths with EJD. Still talking about differential equations. Having rounded off with first order ordinary differential equations, now we go ahead to look at second order ordinary differential equations. So this is an introduction to that. So a second order ordinary differential equation, ODE, is one that contains the second derivative of an unknown function. Okay. It appears in various scientific and engineering problems where the rate of change of a system depends on both its current state and its rate of change. Okay. The general form of a second order ODE is y prime prime, that's the second derivative, plus p of x y prime plus q of x y equals r of x. Of course, you have order 2 and lower orders, right? But the highest order determines its order, which is order 2 in this case. So this is the general thing where, first of all, y is the unknown function. That's like d squared y dx squared. Y is the unknown function of x. Okay. And then we have y prime as the first derivative. Y prime is the first derivative of y. Then y prime prime is the second derivative of y, and it's the highest derivative in this situation. Okay. Um, and then we still have p of x, p of x, q of x, and r of x are functions of x. They are functions of the independent variable. Okay. Now, having looked at that, can we switch gear to consider another vital aspect? Okay. So let's look at homogeneous versus non-homogeneous equations. Okay. So, first of all, talking about homogeneous equations, homogeneous equations. So from what we see at the top here, right, we have this R of X. So whatever R of X is determines whether it is homogeneous or not. Okay. So if in that case, if R of X is equal to 0, the equation simplifies to y prime prime plus P of X, Y prime, plus Q of X, Y equals 0. So in this case, we say it is homogeneous. All right. So if R of X is equal to 0, the equation simplifies to that. And then we can say that the solution is typically found using the characteristic equation if the coefficients are constant. If the coefficients are constant. So we are going to consider this in the next video. So watch out. Okay. For variable coefficients, right? It's possible to also have variable coefficients. Like, we are saying we can use characteristic equation if P of X is constant and Q of X is constant. That is, it is maybe a number without X. But then if it contains something like, maybe if it's not like 2X, 3X squared and things like that. So for variable coefficients, methods such as reduction of order or power series expansion may be used. Power series expansion may be used. Okay, so let's talk about non-homogeneous equations, which are a bit not as easy as homogeneous equations. So non-homogeneous equations. So if R of X is not equal to 0, the equation has an external forcing. The equation has an external forcing function. Okay. So in that case, we'll have a general solution. So we have the general solution, right? The general solution consists, the general solution consists, maybe I can put it this way. The general solution Y consists of the complementary, it consists of the complementary or the homogeneous, right? It consists of the complementary or the homogeneous part, the complementary or homogeneous solution, which we can call Y sub C, and a particular solution, and a particular solution, and a particular solution, Y of P. So in all, we have that Y is equal to YC plus YP. Okay, that's how that goes for non-homogeneous. Now, um, in this situation, we can then talk about another thing, which is the common solution techniques for this. So common solution techniques include the the method of undetermined coefficients. The method of undetermined coefficients. Okay, the method of undetermined coefficients. In this case, that is if R of X has a simple form. If R of X has a simple functional form, and we also have variation of parameters for more complex cases. for more complex cases. Okay. Of course, there's still we also have the D operator method. The D operator method can also be used. The D operator method can also be used as a solution method. Okay. So in subsequent videos, we are going to be looking at all of this. Well, I'm I'm going to talk about applications of second order ODEs in the last video under second order differential equation. So let's watch out for that. So, but of course, for now, we have it coming up in mechanical vibrations, electrical circuits, structural engineering, fluid mechanics, and quantum mechanics. So that's fine. So let's talk now. Let's talk about solution techniques, some kind of overall solution techniques in this case. Okay. Um, solution techniques. Solution techniques. Okay. Depending on the equation type, various methods are used. Various methods are used. You know, I've mentioned some specific methods for non-homogeneous, right? But then we have this is in this aspect we are talking about a kind of generalization of the methods, like a broad classification of the methods. So depending on the equation type, various methods are used. So first of all, we have what you can call the analytical methods. We have the analytical methods. So these include things like characteristic equations, characteristic equations for the homogeneous parts. Okay. We have undetermined coefficients, undetermined coefficients for the non-homogeneous parts. Then we also have D operator, like I said before, also for the non-homogeneous parts, D operator. Then we also have the variation of parameters, method of variation of parameters, method of variation of parameters. So these are all analytical methods. So apart from analytical methods, we have what you can call the transform methods. Transform methods. So we use some established transforms. So a very good one is Laplace. You have the Laplace method. Laplace transforms help in handling Laplace transforms help in handling initial conditions systematically. Systematically. So as we proceed here, I'm going to talk about Laplace transforms, and I'll make it a playlist which will still be added to this because it deserves to stand alone for sure. Then, apart from analytical methods and transform methods, of course, we have numerical methods, which I've done justice to clearly under numerical analysis. So, you want to check out the playlist. It's a long playlist of over 70 videos, because I also joined numerical optimization techniques to it. So we have numerical methods. So this is already settled. Here we have methods like Euler. We have Euler's method. We have Runge-Kutta methods. Runge-Kutta, Runge-Kutta methods. And we have finite, finite difference, finite difference methods. Okay, I mean, I've not been adding method all along, so it's cool. So we have uh okay, let me just say Euler, Runge-Kutta, finite difference, right? So these approaches are useful when analytical solutions are difficult to obtain. And that was like precursor to the whole numerical method thing I did. Okay. So we need to understand finally that second order ODEs play a crucial role in modeling and analyzing real world phenomena, making them a core topic in mathematics, physics, and engineering. All right. So if you have subscribed to this channel, thank you. If you have not, please go ahead and do that right away because in the next video, I'll be talking about the characteristic equation method for solving homogeneous second order differential equations. And you don't want to miss out on that at all. So hit the notification bell and so you can always get notified anytime a new video is released. Then in the comment, let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. And don't forget to like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. So watch out for the characteristic equation method in the next video. Bye.